While human mathematical theory exists in an abstract, unbounded space, computer architecture requires rigid, predefined boundaries to map logic onto physical memory. Java is a statically typed language. Its compiler makes zero assumptions about your intent. It strictly enforces lexical and operational rules before a single calculation happens. Look at this source code for reading basic user input. The syntax is dense because every word is an explicit instruction for memory allocation and tool linking. Standard tutorials focus on building working programs, but to succeed in a professional or academic environment, you must spot the edge cases and compilation errors hidden within this strict syntax. You have to stop reading code like a human and start parsing it like a compiler. You need to build a mental memory ledger, evaluating state changes and type limitations line by line. Let's trace a program execution, starting at variable declaration. Here we see double radius. Declaring a variable tells the compiler to reserve a specific memory block. Notice the box is empty. No value is assigned yet, but the space is claimed. Looking at this table of numerical data types, we see exactly how big that space is. A double strictly allocates a 64-bit block of memory, governed by IEEE 754 standards. The compiler needs a way to reference that 64-bit block. We give it a name. Formally, this is called an identifier. This slide outlines the rules for identifiers. You are restricted entirely to a sequence of letters, digits, underscores, and dollar signs. There is a specific constraint to remember. An identifier can never begin with a digit. While radius 1 compiles, one radius triggers an error. Additionally, reserved keywords like true or false cannot be repurposed as identifiers. Those are compiler laws. Naming conventions, however, are just human agreements. For example, we use camel case for variables and capitalize the first letter of every word for classes, like compute area. For constants, the convention is all uppercase with underscores, locked into place by the final keyword, so the compiler prevents any reassignment. Breaking a naming convention just makes your code harder to read. Breaking an identifier character rule causes a hard compilation failure, the first hurdle in verifying any block of code. Moving to the next line in our execution trace, we hit the assignment statement, radius equals 20. The 64-bit memory block we allocated earlier actively updates to store this specific numeric value. The number 20 here is a literal. As this slide states, a literal is any hard-coded constant value appearing directly in the source code, like 34, 1 million, or 5.0. This creates a specific lexical situation. By default, the Java compiler treats every whole number integer literal as the 32-bit int data type. To allocate a larger 64-bit literal, you must append an L. This is why an uppercase L is preferred. A lowercase l can be easily confused with the digit 1. If you assign a literal that exceeds the capacity of the variable type, the code fails to compile. Look at the statement byte b equals 1000. Returning to our numerical data types table, we see a byte is an 8-bit signed container. Its absolute maximum value is 127. The literal 1000 physically cannot fit. You must constantly verify that the incoming literal perfectly fits within the boundaries of the allocated memory container. The compiler now reaches the calculation step. Area equals radius times 3.14159. The arithmetic is performed, and the resulting floating point value is written into the area memory block. This table shows the standard numeric operators. Addition, subtraction, and multiplication largely execute the way you expect. Division, however, requires closer inspection. Consider the expression 5 divided by 2. While we expect 2.5, the Java compiler yields exactly 2. When both operands are integers, the decimal is truncated and discarded. To preserve the fraction, you must ensure at least one operand is a decimal, such as 5.0 divided by 2. To retrieve that discarded remainder mathematically, you use the modulo operator, represented by a %sign. 5 modulo 2 yields 1. This is frequently used for specific time-based calculations, like converting total seconds into minutes and extracting the remaining seconds. Floating point precision introduces its own nuances. This slide demonstrates that 1.0 minus 0.9 outputs a long string ending in 9998 rather than exactly 0.1. While integers are stored exactly, floating point numbers are binary approximations. Testing doubles for equality often yields unexpected results. Every arithmetic expression must be evaluated strictly through the mechanical rules of its data types, rather than the assumptions of pure mathematics. Programs eventually need dynamic user input. Step 1 is creating a scanner object. The command newScannerSystem.n configures a dedicated tool that links the standard keyboard input stream to the running application. The scanner doesn't just grab raw text. As this table outlines, you invoke type-specific methods like nextInt or nextDouble to match the incoming data to your pre-allocated memory container. Because Scanner is an external utility, you must link it to your program using an import statement at the top of your file. You can either name the specific class you need or use a wildcard to include the entire package. The asterisk acts as a wildcard, telling the compiler to make all classes within the java.util directory available for use. A common misconception suggests that wildcard imports decrease runtime performance. In reality, there is no difference between an explicit or implicit import. Imports are organizational directions for the compiler during the build phase. They do not impact the speed of the final running program. Mastery of Java begins when you stop interpreting code contextually and start viewing it mechanically. To build a flawless mental model, enforce 3 rules. First, audit every single identifier for illegal characters or reserved keywords before evaluating the logic. Second, verify that every literal assignment physically fits within the bit boundaries of its defined primitive type. Third, never trust a mathematical operator at face value. Scan actively for integer termtation and the behavior of floating point approximations. Maintaining this strict line-by-line mental ledger eliminates the ambiguity that leads to common coding errors. Approach your next block of code not as an author reading a story, but as a compiler parsing a series of explicit state changes. By focusing on these underlying mechanics, you ensure your code is syntactically sound and performs exactly as the compiler demands.